Now we are going to discuss on three-phase bridge inverter. The bridge inverters are basically used in order to provide adjustable frequency power to the various applications. So a basic three-phase inverter is nothing but a 6-step bridge inverter, which is shown over here. The thyristors T1, T2, T3, T4, T5 and T6. And it basically consisting of 3 half bridge inverters which are arranged side by side, that is 1, 2 and 3. And the three-phase load is assumed to be a resistive load here, and therefore the function of the diodes will not come into picture while doing your explanation. And a large capacitor is also connected across the DC voltage in order to make the input DC voltage constant, and it also suppresses the harmonics which is fed back to the DC source. And the thyristors are being numbered in a particular sequence, and they are fired at a sequential manner in order to obtain the three-phase voltages VAB, VBC and VCA. And there are basically two modes of operation, that is, one is 190 degree conduction and the other one is 120 degree conduction. First we will be discussing on 180 degree conduction. In the case of 180 degree conduction mode, each SCR will be conducting for 180 degrees. That is, the thyristor pairs T1, T4, T3, T6, T5, T2 are turned on at an interval of 180 degrees. So therefore, I have marked over here 1, 2 and 3 columns. So the first column is 60 degrees, then 120, then 180, 240, 300, 360, again repeating from 60 to 360. Now we said that from each arm the thyristor will be conducting for 180 degrees, that is T1 and T4 are conducting for 180 degrees. So that I will mark it over here. So T1 will conduct for 180 degrees, then T4 will be conducting for another 180 degrees. So it is T1 and T4. Then again T1 for 180 degrees, and again T4 for 180 degrees. Now the thyristors in the upper group, that is T1, T3 and T5, conducts at an interval of 120 degrees. So this is 60, this is 120. So after T1, which conducts for 120 degrees, I will turn on T3. And this T3 will be conducting for 180 degrees. 1, 2, 3. So again we have said that along the thyristor pair T3 and T6 each will be conducting for 180 degrees. So after T3, T6 will be turned on. 1, 2 and 3. Again T3 is turned on for another 120 degrees. 180 degrees. 1, 2, 3. 3 into 60 is 180 degrees. So here T6 will be there. Then again the next set from the upper half, that is T5, will be turned on after 120 degrees of conduction of thyristor T3. So therefore 1, 2. So here I will be turning on thyristor T5. It will be conducting for 180 degrees. Along with the T5, the thyristor pair is T2, which is conducting for 120 degrees after T5. So 1, 2, 3. So here T2. After that again T5. So previously before T5 it is T2 is conducting. So this is T2 and this is T5. So now this is our conduction periods of each of the thyristors. So now I will be mentioning the steps over here. This is step 1, step 2, step 3, step 4, step 5, step 6. And I will mark the conduction thyristors over here. It is 1, 6 and 5. After that, for the next step 60 to 120, it is 1, 6 and 2. For the third step it is 1, 3 and 2. Now we can complete the entire sequences. Now our intention is to define what is meant by a 6-step inverter. So each thyristors would be gated at regular intervals of 60 degrees in proper sequence. So here 1, 6 and 5, then 1, 6 and 2. So 5 turned off and 2 came into picture. After that 1 and 2 remains on, and then 6 is turned off and 3. So in order to get a complete 360 degree, we'll be having a 60 degree steps of 6 pulses will be there. So that is indicating 1, 2, 3, 4, 5 and 6 steps. So again that will be repeating in order to get the total output voltage. We have named our thyristors in such a fashion so as to get a continuous sequence of firing of thyristors from T1, T2, T3, T4, T5 and T6. So if you are considering the instant at which each thyristors are turned on, so first T1, then T2, then T3, then T4, then T5, then T6, like that it is continuing. So for every 60 degree duration only 3 SCRs will be conducting, and you can observe that T1, T6 and T5. So T1, T6 and T5 during the first step. So in that case 2 thyristors from the upper half and 1 thyristor from the lower half is conducting. This we will be redrawing in such a sequence for ease of explanation. So we have our source voltage Vs, then the thyristors I have named it as 1, 3, 5, 4, 6 and 2. That is for the conduction from 0 to 60 degrees. So T1, T5 and T6 are conducting for the period of 0 to 60 degrees. So that I have marked over here thyristor 1, thyristor 5 and thyristor 6. Rest all the switches are in the open condition. Now you can see the load, 3-phase load, which is connected to the common terminals A, B and C over here. So this is the A terminal, which is corresponding to VA, which is connected over here, and since the thyristor T1 is in the on condition, this point A is connected to the positive terminal of the source voltage. Similarly, here we can observe that 5 is turned on, which is connected to the point C, and therefore we can say that C is also connected to the positive terminal of the source voltage. So I will mark over here A and C are connected to the positive terminal of DC voltage. Now the point B is connected to the lower half thyristor T6, which is connected to the negative terminal. Therefore I can write it as negative, connected to the negative terminal of DC voltage. We will mark the load voltage. So load voltage is VAB VBC and VCA. Now here it is from the point A then to the point B, and similarly again from the point positive terminal to the point C and to the point B. So two voltages which comes over here, it is VAB and VCB. So B is the common terminal because it is connected to the negative point. So plus Vs is coming to A and negative to the point B. So VAB is nothing but Vs. Similarly, you can observe it here. Plus terminal is connected to the point C, negative terminal to the point B. So it is also equal to VCB. So there are two voltages, VAB and VCB. Now I have again redrawn that one. So Vs. So across the point A and C, the same voltage is coming, and that is the plus voltage. And the negative terminal, it is connected to the point B, and we have the impedances which is marked as the Z, and this is the star point. Now you need to find out the voltage across VA0, VC0 and VB0 in order to find the three-phase voltages VAB, VBC and VCA. So here I have marked the total current as I1. So I need to find out the current I1. I1 is equal to Vs divided by the total impedance. So here two impedances are in parallel and they are the same, so it is Z by 2, and here it is Z. So totally it is Z plus Z by 2, that is nothing but 2 by 3 into Vs by Z. Now I need to find out what is the line to neutral voltages. So the first one is VA0. Since they are connected in parallel, it is also equal to VZ0. VZ0 is equal to, we are using the voltage division rule, I1 into Z by 2. So the total current is passing through the impedances, and across these 2 points the total impedance is Z by 2. So the total current I1 into the equivalent impedance between these 2 points is nothing but I1 into Z by 2. So I1 is already obtained as 2 by 3 into Vs by Z. Therefore I can write it as Vs by 3. Now we need to find out VOB. The current I1 is coming through this impedance Z. So therefore I1 into Z, which is nothing but 2 Vs by 3. This I will mark it over here. This is Vs by 3, which is nothing but VA0 or VC0. Next is VOB, which is 2 Vs by 3. So I have the line to neutral voltages VA0, VC0 and VOB. Now we need to find out the line voltages. First one is VAB, then VBC, then VCA. So VAB is nothing but VA0 minus VB0, which is nothing but Vs by 3 minus VB0 we need to write down. Here I have written as VOB. So VB0 is nothing but minus 2 Vs by 3, which is equal to Vs. Now VBC is again nothing but VB0 minus VC0, which is equal to, here I have written as VOB, so VBO is nothing but minus 2Vs by 3 minus VC0 is nothing but Vs by 3, so it is Vs by 3. So here it is again minus Vs. VCA is nothing but VC0 minus VA0. VC0 and VA0 both are equal, that is Vs by 3 minus Vs by 3, which is equal to 0. Now in order to draw the waveforms, what we need is, one is VAB, which is equal to Vs, then VBC, which is equal to minus Vs, and VCA, which is equal to 0. Then you need to have the line to neutral voltages. If you want to draw, it is VA0 and VC0, it is Vs by 3, and VOB is nothing but 2 Vs by 3. Now this we will be drawing onto the waveform chart. So this is VA0, VB0, VC0, then the line voltage is VAB, VBC and VCA. So we are drawing it for the step 1, that is from 0 to 60 degrees. We have seen that VA0 is equal to Vs by 3. So VA0 is equal to Vs by 3. That I will mark it over here for 0 to 60 degrees. During that interval, VC0 is also equal to Vs by 3. That will also marked over here it as, along the VC0 I will mark it as Vs by 3. Now I need to mark VOB, which is 2 Vs by 3, and here it is VB0. So there the value is minus 2 Vs by 3. So this I will mark it as minus 2 Vs by 3. So this is 0 point, so minus 2 Vs by 3, and this is Vs by 3, this is also Vs by 3. So that is for the period of 0 to 60 degrees. So during that time we also need to write down the value of VAB, VBC and VCA, and which is very simple. VAB and VBC both are Vs and minus Vs. So VAB is plus Vs and next is VBC, which is minus Vs. So this is VBC, this is 0, so this is minus VC. So during that instant VCA was 0, so this I will mark it as 0. So this is minus Vs, this is plus Vs. So we have drawn the waveforms for the period from 0 to 60 degrees. Now we need to draw it from 60 to 120 degrees, that is the step 2, while considering the thyristors 1, 6 and 2 in the on state. That is 1 from the upper half and 2 from the lower half are in the on position. This we will draw it like this. Draw it for ease of explanation like this, where T1, T2 and T6 are conducting, that is 1, 2 and 6 are conducting. And for ease of explanation we have drawn like this. We have a star connected load, VA0, VB0 and VZ0, the voltages. So T1 is conducting, T6 is conducting, T2 is conducting. So here again you can observe that A point is connected to the plus terminal. So I'll write A is connected to positive. Now T6 and T2 are in the on position. So this point is C is connected to negative. Again this point B is also connected to negative. So B and C are connected to the negative terminal. Now we need to write down the corresponding voltages VA0, VB0 and VC0. So here you can observe that VB naught and VC naught are the same. So I have again redrawn the previous figure with the on-state thyristors only. So it is Vs connected to the point A, B and C are connected to the negative terminal, and this is the star point. Now I have marked this current as I2. So this I2 is nothing but total Vs divided by total impedance. So Z divided by parallel, it is Z by 2. So it is Z plus Z by 2, that is nothing but 2 by 3 into Vs by Z. Now we need to draw the line voltages. So it is VA naught is equal to I2 is the current, Z is the impedance. So I2 into Z, which is nothing but 2 by 3 into Vs by Z into Z. So it is 2 by 3 Vs. So this I will mark it as 2 by 3 Vs. Now the next level of voltages we need to find is VOB and VOC. Both are the same because they are connected in parallel. So I will write it over here. VOB is equal to VOC equal to the total impedance is Z by 2, and since it's a parallel connection, the voltages will be same across the branches, and therefore I can write it as I2 into Z by 2. So which is nothing but I2 into, so I2 is nothing but 2 by 3 into Vs by Z into Z by 2. So it is Vs by 3. So I will mark it over here it as Vs by 3. Now we need to find out the line voltages. So it is VAB is equal to VA naught minus VB naught, which is equal to VA naught is nothing but 2 by 3 Vs minus VB naught. I have obtained it as VOB. So VB naught is nothing but minus Vs by 3. So it is minus Vs by 3. You will get it as Vs. Now we have obtained all the line voltages VBC and VCA. So here you can see that VAB is Vs, VCA is minus Vs, and VBC is 0. Similarly, VA0 is 2 by 3 Vs, and VOB and VOC are Vs by 3. I can also mark it as VBO, which is equal to VCO, V is equal to minus Vs by 3. So these quantities we will be marking it over in the waveform chart. Now from 60 to 120 degrees, T1, T6 and T2 are conducting, and we have obtained the corresponding phase voltages and the line voltages, which we will mark it in the waveform. So VA0 is 2 by 3 Vs. So VA0 is 2 by 3 Vs. So it will be going to the top, and this is 2 by 3 Vs. During that time, VB0 and VC0 are minus Vs by 3. So this is VB0. It was earlier minus 2 Vs by 3. It has reduced to minus Vs by 3. So this is minus Vs by 3. And VC0, it has changed from Vs by 3 to minus Vs by 3. Now you need to find out the line voltages. VAB is Vs. So VAB, earlier it was also plus Vs. Now it will be continuing for another 60 degree Vs. So during that time, VBC, earlier it was minus Vs. Now it is 0. Now VCA, VCA is minus Vs. So it has changed from 0 to minus Vs. So during the period from 60 to 180 degrees. Now in the same fashion, how we have marked for step 2, we need to draw it for step 3. So for step 3 it is, the thyristors conducting are 1, 3 and 2. We need to find out the line voltages and the phase voltages, and you have to draw it to the waveform. And now we will be seeing the complete waveform after one set of firing of thyristors are completed. Step 3 it is 1, 2 and 3 are conducting. During that time VA0 is Vs by 3, VB0 is Vs by 3 and VC0 is minus 2 Vs by 3. So during that time VAB is 0 because it is VA0 minus VB0. So VA0 and VB0 both are equal, and therefore VB0 is VAB is 0. So now you can complete the entire 3-phase voltages also. You can also observe that each voltages are shifted by 120 degrees. So this is 120. After that VBC comes. Again after 120 degrees VCA comes. So this is how the operation of a complete 3-phase inverter with 180 degree conduction mode happens. Thank you.